So I would like to start by thanking you for coming here after so much trouble. There was a lot of delays and planes and such, and I really appreciate for you coming here. Welcome to ICOS and welcome to Macedonia. I would like to first start by looking back. When we met 3 years ago and enjoyed the amazing New York food and the busy streets of Manhattan, hardly anyone could have imagined how much the world would change in just a few months later. So we could not have predicted that colleagues and families would become isolated, students would become separated from their teachers and classmates, and life will become so much more difficult than we used to be. Not many of us could have predicted that the process of globalization could be reversed, and more recently that we would enter an era of a turbulent and politically increasingly divided world. In a post-pandemic society where the flow of ideas, people, and goods has been restricted without precedent in the modern history, it is absolutely essential, more than ever before, for our dynamic research community to come together, to be able to interact, discuss, and reconnect. And this is exactly the spirit of this conference, where we selected this theme, Rebuilding Bridges, as a highlight of our determination to bring our community together again. So I would like to start first with congratulating all of us for setting a milestone in ICOS conference as we celebrate half a century of ICOS conferences. And I'm particularly honored and proud that for this event we can host you in my homeland, Macedonia, which has always been a bridge between the East and the West, and whose people are known for their hospitality. The selection of the site for this year's conference goes beyond this country, being a cultural melting pot and a crossroad of civilizations. As you could probably sense from the contents of the scientific program that you already have, in this meeting we focused on including a good number of both junior and established speakers from Southeastern Europe, who otherwise, from financial or visa-related or other issues, might not have been able to attend previous ICOS meetings. I can assure you this region has provided a lot to this community by having some of us, and many of us actually sitting in this audience, pursuing their professional aspirations by working in reputable academic institutions worldwide. And I happen to be one of them. So, going into more details, I would like to mention what is old and what is new in this conference. Based on the experience from the previous ICOS meetings, first, we decided to retain the overall format of the conference, with sessions that for these sort of specialized meetings are rather loosely defined, and in many cases they are overlapping. We retained the 20-minute introductory notes by the chairs and the co-chairs, which in our own experience are a very effective approach to bringing up to speed participants who are not familiar with a specific session topic. We also decided to retain the generously long coffee breaks to ensure a sufficient time for discussion and interaction, of course with face masks that I can see nobody is wearing at the moment. So what's new in this conference? The novel aspects that we introduce are greater number of plenary speakers and the new role of a session co-chair. And the intention with this change was not only to ensure a better geographic and gender balance, but also to be able to introduce junior researchers to that capacity and to expose them to an organizational experience. We also tried to make this conference financially accessible within the planet expenses, of course, and especially to researchers from the region who might have limited access to research funding, and we also provided financial support for women researchers. Now, I would also like to remind all the participants at the ICOS meeting that this series has a zero-tolerance policy to any form of harassment, and that includes sexual harassment, and that we abide to the IUCR policy of freedom of scientific expression, which is stated, and you can find it on the conference website. As a second important requirement, although currently in Macedonia it is not mandatory by law, we would like to request that all participants wear face masks when they are in closed spaces. especially during the lectures. As it has become clear with some recent post-pandemic conferences, the chances of spread of COVID in smaller groups of people who travel from different countries and interact closely over a prolonged period of time are significantly higher. So we have, for that purpose, provided each participant with a COVID test kit at registration. We would encourage you to self-test today after your arrival. And in case you need another test kit, just let us know and we will provide it for you. If during the conference you start to experience any COVID-like symptoms, we would request that you remain in your room and let us know about that. We will provide additional test kits for you throughout your isolation period, and of course we'll provide food for you, so you won't remain hungry. Now I would like to mention something about diversity. For those of you who have participated in the past meetings of this series, they will recall that the ICOS series has a very good history of being diverse and inclusive. And with this meeting, we made the best efforts to continue that tradition. So we have 116 registered participants coming from 23 countries, with most participants coming from the UK and USA, followed by the UAE, Germany, Israel, and other countries, with a rather favorable female-to-male ratio and also age distribution. Also, working closely with our session chairs and co-chairs, we attempted not only to select excellent speakers, but also to maintain a balanced cohort of speakers with respect to gender, age, and geography. In consultation with our chairs and advisory board, we have selected 82 speakers, with very close number of male to female speakers in the final speakers list. Unfortunately, our confirmed speakers from China were not able to participate due to COVID-related restrictions on international travel. I would also like to mention here that this community has always been inclusive. So in addition to talks that focus exclusively on organic molecular materials, we have also included a number of talks that focus on crystallization, structure or properties of inorganic and metal-organic or metal-containing materials. And I particularly like to show this slide because for the first time we have also some award recipients here. I would like to heartily congratulate on the recipients of two different types of awards. The first one is the ICOS Award for Young Researchers, which is sponsored by the International Union of Crystallography. And for the first time, we have also introduced the recipients of the ICOS Award for Women Researchers. So congratulations on the winners. Moving on to our plenary speakers. We are delighted to have 4 fantastic plenary speakers coming from 4 different continents, which reflect, in some way, the past, present, and future of the organic solid-state research. With this conference being the 50th anniversary of ICOS, we will get started by looking into the past, as always. And I'm thrilled that our first speaker is Craig Eckhart, who, goes without saying, comes with an outstanding contribution to the organic solid-state research community. Craig has kindly offered to lead us through the past half a century of evolution of the solid-state research, something that those of us like myself who have joined this field much later need to be aware of, to cherish and build upon in our future research endeavors. After plenary lectures by our stellar Aurora Cruz Cabeza and Professor Masako Kato from Japan, we will wrap up the conference with a plenary by Len Barber, who, as I'm sure you will agree, does not need a special introduction. Len is currently in Belgrade and his flight was delayed for tomorrow, so we will meet him tomorrow. With his decades-long experience and being one of the most impactful researchers in our field, Len will lead us into the future of the solid-state chemistry. So we're going to start with the past and we're going to end with the future. I'm confident that his lecture, as always, will encourage the young, talented individuals in this audience to become active members of our community. And also, it will be a reminder that it is precisely them that we rely on to continue the legacy of this half a century of tradition. Now I'm going to switch my cap to a tour guide, and I will tell you more why we are here and why Ohrid is such a big deal for us. So I'm going to start also by looking at the history. This small town happens to be one of the oldest human settlements in Europe. It covers layer upon layer of history, and its significance expands much beyond the borders of Macedonia, and is considered a religious and cultural center of Eastern Europe by the Slavic people in general. First, I would like to invite you to visit the Museum on Water called Bay of the Bones, where human settlements on water date back as far as 1200 BC, and they were reconstructed. Then we have the ancient theater from around 200 BC, and which is one of the best preserved amphitheaters in Macedonia, and which was used for gladiator fights. The actual old town was built mostly between 7th and 19th century, and it has been preserved as one of the most complete ensembles of ancient urban architecture in this part of Europe. Also, Ohrid was once an important trading center on one of the most famous ancient roads across Europe, Via Ignatia, which was the main road connecting Istanbul on the east with Rome in the west, which goes along with this region being a bridge between two divided worlds, and also with a conference theme. And as a testament of a little bit of more recent history, I'd like to invite you to visit the well-preserved fortress of Tsar Samuel from the 10th century, which is located on the hill above the town. So how about the lake? Ohrid Lake is the oldest lake in Europe, and it has been also believed to be one of the 3 oldest in Earth, together with Lake Tanganyika in Africa and Lake Baikal in Russia. These crystal waters that you see in front of you have existed continuously for approximately 1.4 million years. And that was a sufficient time to develop what's now a living museum of endemic forms. The oligotrophic waters of the lake conserve over 200 species of plants and animals that are unique to the lake, and this includes algae, flatworms, snails, crustaceans, a unique round sponge, and very important to those of us who fancy fish, the endemic and very delicious Ohrid trout, which you will recognize by these freckles on the back. At the current state of research, 176 species of the lake are endemic and can be found only in these waters, and that constitutes about over 70% of the total flora and fauna of the lake. Now, there is another dimension of Ohrid, and that is Ohrid being a cultural and religious center. I will tell you a story to just give you the short version of why this is so important to us. There were 2 brothers, Cyril and Methodius, which were born in Thessaloniki, which is now the Greek part of Macedonia, who were philosophers, theologians, and missionaries, and they were requested to invent a new alphabet that was called Glagolitic alphabet. One of their disciples, Clement of Ohrid, simplified this alphabet, and in honor of one of his teachers, called the new alphabet the Cyrillic alphabet. He was also founder of the Ohrid Literary School, which is considered the first Slavic university and was established nearly 1,100 years ago. Remind you that this is exactly 202 years before University of Bologna, Alma Mater Studiorum. So in some way, Ohrid was for the Eastern world what is Bologna for the Western world at that time. As a result, Ohrid became a center where all the best professors, bishops, and archbishops were educated. They spread Slavic literature, culture, singing, and art from the Balkans to Europe and Asia. In 2007, with accession of Bulgaria to the European Union, the Cyrillic alphabet became the 3rd official script of the European Union, following Latin and Greek. The Cyrillic alphabet nowadays is used by around 250 million people in Eurasia as official alphabet for their national languages, of course with small variations. So you can see how important this small town has been in the past. Now I would like to switch to people who are standing behind this conference. And I would like to take a moment to express my deepest gratitude to the members of the organizing team, who are also happen to be members of my research group. They have done an incredibly excellent job in making this possible under the extraordinary conditions of decreased funding and limited travel as we experience today. And I would like to thank them for being my strongest support and for sharing this excitement for solid-state research with me. This is your conference, and I hope you enjoyed the results of your dedication and hard work over the past year or so. I would also like to take a moment to acknowledge the support from the members of the local organizing committee who have been working on site to ensure smooth organization, even in the absence of the entire organizing team from the country. So we were back in Abu Dhabi, but while they were working on site. And special thanks here go to our amazing chair of the local organizing committee, Professor Lyub Chopeov, who has been in many ways the key person in making this event happen here in this country. Thank you, Lyubcho, for your dedication. And thank you for your tireless efforts and enormous time you have spent in going to the administrative labyrinths of the country to set the legal and financial framework for the conference. You are inspiration to many of us. You might also ask yourself what the conference logo means. You'll find it everywhere, even on those bottles of wine that we shared with you. The logo actually is a combination of three different themes. So it's a combination of the lake, this blue circle, the cupola of the church of St. John of Caneo of 13th century, which is an iconic church built on a cliff. And it is probably one of the most photographed places in Macedonia, which this cupola actually reminds me of a crystal, which is why we selected it as the main theme. And the third component is the sun, which has been always the ancient symbol of this country. So I also would like here to say something about the new award that we established. Since this year, we established the first Joel Bernstein Memorial Poster Award to honor the legacy and contributions to this community of our colleague and dear friend, Joel Bernstein. You can see here a picture of him and his wife here in 2017 on Ohrid. So one of the poster presenters at the end of this conference will go back with this award and significant financial support. All right, so I would also like to give you a few pieces of useful information. You'll find all this in abstract book, but basically we have a shuttle bus that will start operating from tomorrow on. It will go 5 times between the conference site and the town. These are the timings. Feel free to jump on and explore. Hopefully we will not see this hall empty here during the conference. But also, if you have time, or if you're staying before or after the conference, there is so many other outdoor activities to do here, and they are listed here. So please feel free to contact our logistical support, Mr. Pero, and ask him if you would like to take part in some of these activities. And also, if this was too much information for you, I would like to give you maybe a short version of it. What do you need to do in Ohrid? First, architecture. Try to enjoy. This is a very typical Macedonian architecture that you would not find elsewhere. Second, try the local food. And you can see here the endemic trout somewhere there in the middle. It's very, very good. And also the third, you should buy pearls. Ohrid is very famous for pearls because they are made by a secret recipe by only 2 families, and they have kept their secret for a long, long time. And I heard that even Her Majesty has some of them in her permanent collection. So finally, I would also like to give you a few other pieces of information. First, we decided to streamline this conference just a couple of days ago. If any of the speakers does not feel comfortable with their talk being streamlined, please do let us know in advance and we will exclude you from this process. Basically, what we wanted to do is to have a wider outreach for those people who are not able to travel from financial, visa, or other issues, and especially to students who are also sometimes left out from these long travels. Second, if you found that weird question, do you consume alcohol, in your registration form, that is not because we care whether you drink or not, but because if you do, you would find a small present in your room, which should provide the taste of the Macedonia in addition to the view of this beautiful place here. So enjoy your bottle of Macedonian wine. And the third unimportant information is that in front of this hotel, on the left side, you will see a couple of guards. That is actually the summer residence of the Macedonian president. And don't feel free to just stop over and say hi. If you see him swimming, say hi, we are from the conference. Yeah, I'm sure he will be happy to hear about this event. All right, and finally, of course, I would like to thank everyone who participated in this. First of all, the session chairs and co-chairs, which were of great help to us to select amazing speakers for this conference. All of the speakers were consulted with the chairs and co-chairs. I would like to thank the ICOS Advisory Board for helping us in a decision-making process, especially with the awards and the postponing of the conference for 1 year. I would like to thank the organizing team and the local organizing committee, as I already mentioned. And finally, I would like to thank you for coming so far to this event. It's really important for us community to get together and to be able to interact in person as opposed to online. And obviously, I have to acknowledge the contribution from our sponsors, with the Rigaku being our gold sponsor. So thank you very much again, and I will hand it over to my colleague Miguel Garcia Garibay, who will introduce our first plenary speaker. Thank you.
Okay. Well, first of all, thank you, Panche. Clearly, it's just incredibly pleasant to see all of you, to be able to meet together again in person, and to do it here in Ohrid, thanks to Panche, I think is a very special treat. So in addition to thanking Panche and his group for putting all this together, I think the local organizing committee also should be acknowledged. I think clearly this is, I organized ICOS in 2005, so I know what it's like. It's a lot of work, but it's a lot of satisfaction to see this community and to be able to share the science that is shared here. When Panche asked me to introduce the first speaker, I thought that was like a treat for me. So for me to introduce Professor Craig Eckhart is really a very special occasion. Craig is one of the founders and one of the giant intellectual leaders of this community. He's someone who I have admired my entire career, someone I've looked up, and someone who, through his career, also has really promoted young scientists, and I was a beneficiary of that aspect of Craig's activities. Well, you would not be surprised that someone like him has a extraordinary academic trajectory that I'd like to share with you. So Craig received his Bachelor's of Arts magna cum laude with a major in chemistry and a minor in history from the University of Colorado at Boulder. He was holding a Regents scholarships, and he was elected Phi Beta Kappa. So for grad school, he went to Yale University, where he obtained both a master's and a PhD degree. And I think he had an accomplishment that I never heard before. There are two very prestigious predoctoral fellowships that students might get in the United States. One is given by the National Science Foundation, the other one by the National Institutes of Health. Craig had both of them, so he had presumably full support through his graduate studies. So he then accepted a position as assistant professor at the Department of Chemistry at the University of Nebraska-Lincoln, where he has been his entire career. And he escalated the professorial ranks very quickly from assistant professor to associate professor to full professor in about a 10-year period, which is really quite unique and quite rare. A few years later, he was appointed professor of physics, which I can tell you that his scholarship is very rigorously grounded in quantitative analysis, physical chemistry, physics. I am an organic chemist, and I've always found my interactions with him really, really intellectually stimulating because he can talk to all of us, regardless of what our disciplines are. He has had many honors through his distinguished career. So he was a Guggenheim Memorial Foundation Fellow at Cambridge University. He was a Fulbright Senior Fellow at the Wroclaw Technical University. And then he was sponsored by the Korea Science Foundation Genius Program to become a visiting professor at the Pohang Technical University, or POSTECH, in 1997, 2000, 2002, and 2004. So he had an opportunity to be an influential force in the Korean scientific community. He has also been professor at NYU, at the Johannes Gutenberg University at Mainz, the University of Stuttgart, and Milan. He has been, as you can imagine, a very active member of the solid state and material sciences community. He has served on numerous panels in the National Science Foundation. He has chaired a number of conferences in the solid state and co-chaired. He has published, at least that I know of, 3 book chapters and over 115 papers in reference journals. He has directed a large number of PhD and master theses. And his research interests are, in many ways, from the very beginning, a little bit ahead of the time. So he has been interested in the theory of organic solid-state reactions, collective interactions such as emergent phenomena, polymorphisms and phase transitions in 2- and 3-dimensional crystals, mechanochemistry from the very beginning, nanotribology, and the mechanisms of detonation, so solid explosives. He is best known for his experimental contributions in the field, and when I think of Craig myself, I remember one time when he told me that if you want to do a reaction in a single crystal and want to control the amount of absorption, just be mindful of the transition dipole moment of the molecules in there, and use that as a tool. And it kept me thinking. I said, that's really brilliant. But he's been doing specular reflection, UV-Vis and IR, brewing and scattering Raman, and piezo modulation. And today, he has a trick for us. He's going to talk to us about his 50 years with organic solid-state chemistry. Craig.
Okay. Yeah. Here.
Okay, just open. Here. And just up and down.
Okay. That's easy to do. Well, that took some time. I want to thank the organizers for inviting me. It's 50 years does show, I guess, a bit, but it's still an honor to be able to address this conference, which has always been one of the highlights of my scientific activity. The 50 years is not so much my 50 years as, I don't know what's going on here. Huh. Jumped on its own.
This is a second.
Okay.
I will change you.
Well, I don't want to change yet. Okay.
Okay.
It's not my 50 years. Panche charged me with talking to you about the origins of organic solid-state chemistry. And I realized that that was going to be a problem because there's so many good, brilliant workers in the area who do amazing work that I could lead to difficulty with a lot of friends and colleagues. So I've set a criteria for what I'm going to speak about, and that is to have to be dead or be retired for a long time. That avoids a lot of problems, I think. So that's the way I'm going to approach this talk. But I do think we will see how, from this aspect, that the field has grown and what its roots are. To start with, excuse me, this is completely out of order.
Just down.
No, it's out of order.
Yes.
Yeah.
Just down.
Close the screen.
In the end, or it's a beginner.
That's the end. Well, I'll improvise. That's all right.
Yes. This is a
Yeah.
second. Must open.
Okay.
I will change you. When you want to change, I will touch. Just a minute.
No, let me just work it out.
Okay. This is a second.
Yeah.
Okay.
Okay. I don't know what happened. Can we just go to, can we get off the screen a minute? Now let me go to PowerPoint. Now let's close this.
Okay. It's like, do you want to?
No, that's, I don't know what's happening.
Never mind.
Great. Would you feel comfortable that I change the slides for you?
I don't know how it got out again. My advice is don't get old. Avoid it at all costs. Where was I? Okay, so what I've decided to do is present the view of organic solid-state chemistry in its origins, and doing it in two ways. One is to look at experiments, and the other is to look at concepts. And we'll start with, and there's no particular order. But I would say experiment always guides and theory decides. But in this case, there's some very important experiments. The first set of experiments that I think were very important were those by were those by G.M.J. Schmidt and Mendel Cohen on cinnamic acids. They were aware of earlier work, but they were the ones who did the first real chemical viewpoint study of this simple photoreaction. This is cinnamic acid. Oh, I thought I had a laser pointer, sorry. The cinnamic acid, as you see at the top left or right, it will dimerize under photolysis. But it was found that two different monoclinic forms of cinnamic acid would lead to two different dimers. As you can see, one is cis and the other is trans. And it was stereospecific. And the yield was nearly 100%, which hardly ever occurs, as you know, in solution. So this was the first inkling that chemistry in the solid state was interesting because, of course, in solution, you wind up with a 50-50 mixture of the two isomers. Another workers in the field were Ian Paul and David Curtin. Their work is so encompassing, it was hard to, I could talk for hours on just say Curtin and Paul. So I've tried to condense it down to a horrible actually as we'll see, three systems. They I think, their greatest impact was, I think, through their reviews. They had an exhaustive discussion of thermal solid-state reactions. And now, remember, when we talked about cinnamic acid, that was photolysis, that was photochemistry, which is simpler in many ways than dealing with heat. But Paul and Curtin did a masterly job of analysis. But their description was fairly phenomenological, and I think their discussion of what happens was a bit on the naive side. But where they really shone was when they discussed the importance of polar axes in crystallization and in chemistry, solids, and how the polar axis plays an important role in solid-state organic chemistry. And I have a, you can see the one of the papers on the right side there. And there you see those worthy gentlemen. It was a brilliant discussion, I thought, for being non-physical, and it was showed great insight that David Curtin had, especially in the chemical way. Now, this was a dynamic duo team, a kind of Batman-Robin situation, where David was Batman and Ian was Robin, although I think Ian was a little more of a Robin than the Marvel character. But they worked together. Ian was the crystallographer, and most interesting paper was dealing with chemical reactions of crystals with gases, because what they found was very clever experiments that the yield of ammonia reacting with certain organic acids, crystals, yielded had different yields and different products depending on which phase it was reacted with, the ammonia reacted with. Now, this was utterly painstaking work. Another interesting system that led a lot of people to scratch their heads was distyrylpyrazine. This is work at Hasegawa. And Hasegawa's work found that the polymerization of distyrylpyrazine would lead to oligomers in the, if the irradiation was at 400 nanometers or longer wavelength of light. But for wavelengths of light shorter than 400 nanometers, you got high polymer. And it was baffling why that color combination should occur. Well, later work showed that it involved a lot of things. For example, the 400 nanometer transition is an N-to-pi star transition, which is normally a transition of very low intensity, which means a small dipole moment. Whereas the higher energy transition was a large pi-to-pi star transition and very intense. And that was the only thing that was recognizable at the time of the publication of those two. I showed two pictures of Hasegawa because I know there are a lot of young people in the audience. And this is the picture on top is Hasegawa at the time he did the work. Later is when he was Hasegawa, the famous professor. Another interesting system that people puzzled was the polydiacetylene polymerization. This is work by Gerhard Wegner. What Wegner found was that if he took the diacetylene with various R groups, substitution groups, that it would readily and easily photopolymerize. But that geometry was kind of difficult because, as you can see, the lineup in the crystal is more or less this, the single molecules are kind of parallel to each other, and they have to rotate in a concerted fashion to yield a polymer. And that rotation actually is huge, and yet it's a crystal-to-crystal transformation. And that was, of course, was shocking to a lot of people. And it wasn't until people began to think of collective motions that they began to understand how this might occur. So now those are experiments that kind of drove people to think about what was going on, to think about exactly what is driving this chemistry. So the conceptual foundations are the topochemical principle, which results from the dynamic work of Schmidt and the Weizmann work group. The reaction cavity concept also from Weizmann group, mainly that of Mendel Cohen. Steric compression is a work of Mike McBride, I should say. The phonon insistence I only mentioned was work by Paras Prasad, who is not retired and is not, to my knowledge, passed from this mortal veil. So I bring it up only because in the context of the motion of the PDA, the polydiacetylene, this phonon insistence is important because it implies there are vibrational motions of the lattice that would lead to a reaction. And so you must remember that we think of vibrational spectroscopy as vibration of atoms. But when you're dealing with a crystal, the molecules themselves are vibrating against each other. There are modes of vibration that are, which you might say, extreme. For example, when an organic crystal undergoes a phase transition, there's some mode of vibration of the lattice becomes what's called over-damped. That means it just gets really, really big. And so the crystal kind of shocks itself into the the new lattice and the phase transition. So the phase transition of the soft mode is similar for the reaction in polydiacetylenes. So the dawn of the area of the organic solid-state chemistry, in my opinion, started a little earlier than 1940 with the work of J. Monteith Robertson. Robertson was the first crystallographer to just actually solve the structure of a molecular crystal. And as you can see from those experiments that we talked about, all the information that was gathered was information of structure. That would have been impossible without the pioneering work of Robertson. Robertson looked at metal phthalocyanines because he could use the metal to solve the phase factor problem and get a structure. So that was the first step in doing organic solid-state chemistry, because without that structural information, these experiments that we talked about, just talked about, cannot be known because you would know what was happening. Two other founders that are kind of prehistoric in the sense of this field. The first is A.I. Alexander Isakovich Kitaygorsky, who wrote papers before, I should say, but his original book that came out was called Organic Chemical Crystallography. And it was the first, I couldn't find a modern text of it. It was this thing in the lower right corner is the only book I could find that it was from that early text. Most of my friends and colleagues were more familiar with this book, Molecular Crystals and Molecules. Now, Kitaygorsky was a crystallographer and a physicist, but he was especially interested in why molecular crystals form, because, of course, solid-state physics easily understood ionic crystals. Coulomb's law took care of that. And with the work of Sommerfeld and others, metals were worked out also. It's just kind of one gigantic molecule. But what about molecular crystals that are made of these individual entities? Well, Kitaygorsky realized that there are forces involved, dipole-dipole forces, that can be attractive or repulsive. If you look at two dipoles, as you see in the upper right-hand side, there is an attractive part to their interaction, which you see by the crossed red arrows, and repulsive part of dipole interaction. So when dipole line up, you get this partial attractive energy and also a repulsive energy. Now, when you look at this, you say, well, benzene doesn't have a dipole, why do I care? Well, of course, you realize that the electrons are always fluctuating, and we know the London forces are dipole-induced dipole forces, and we can have dipoles just due to fluctuations. Those fluctuations can induce dipoles in adjacent molecules. So still we can get these kind of Lennard-Jones interaction. So I'm sure you're all familiar with the Lennard-Jones potential shown in the graph. But when it does it for a crystal, you have to sum over all interactions. And so you see on the left-hand side, on the right-hand side, the summation sign, those Rij's, those R terms are between every atom in the crystal, which is quite, there are games you can play to do this, but with modern computers, you can be you can just pull it out and do the lattice sum if you know the crystal structure, and you can get the potential holding the crystal together. So Kitagorowski pushed this very early on in the game. Then the next fellow is a Ukrainian, actually, a Ukrainian scientist. Of course, he was in the Soviet Union at the time. He became an outstanding Russian physicist and director of the Soviet physical sciences for materials or solids. And what Davidov did, also Alexander, Davidov did was develop a theory of molecular excitons. So what's that? Well, Davidov realized that just following after Kitagorowski, that they have these dipole-dipole interactions. But Lennard-Jones potentials deal with ground state dipoles. And Davidov realized that, didn't realize, he knew that molecules had excited states where you had transition dipole moments. And those transition dipole moments can interact with each other also. So this interaction would be either parallel or they're vibrating in phase. You can see that's repulsive. And so you can find that from the free molecule, which is the energy level to the far left in the first diagram, it's the free molecule. When it interacts with another molecule, the dipoles, if they're parallel, you'll actually get a shift of the energy level of the system to higher energy. So the dimer transition will be the electronic transition, or even a vibrational, as well as the dipole type transition, will go to higher energy, whereas the lower energy combination, which is also would be anti-parallel, is forbidden, because you can see the dipoles add in the high energy phase or high energy geometry. On the far right side of the diagram, in the middle, you see the head to tail arrangement, and in this case, the head to tail arrangement, you can see now that the head to tail, when they're in phase vibration, that is a lowering of the energy, but it's in phase, therefore it's allowed, and that leads to a lower energy, but allowed. Now spectroscopists have fancy names for these. In the one case, you're talking about the chromic shift, the other, the red shift. But in molecular crystals or in any other system, if you have an oblique arrangement of dipoles, then you get both the lowering and the raising of the band, and the intensity depends on the geometry, the specific geometry of the system. To the right, we see anthracene. The anthracene molecule, you can see, is in an oblique arrangement, and you can see what the spectrum is on the 001 phase, or excuse me, yes, 001. With the light polarized along the A-axis, which is the green light, and light polarized along the B-axis, which is the red lines. You can see there's a split between them. The same as that split you see for the oblique system. Now this again has to be, this is just for two dipoles interacting. If you're doing the crystal, you have to do the same trick you did with the Lennard-Jones system, and you have to sum over all the interactions of all the dipoles. But once you do that, you can calculate the crystal spectrum. And you will find that just as the molecule has principal directions, or has fixed directions in it for absorption of light, so does the crystal, and it's dictated by the crystal symmetry. And each of these symmetry axes in the crystal yields its own spectrum. So these are collective interactions, collective excitation of the crystal. Now this explains the DSP work, because in DSP, the molecule is oblique to each other. The reacting molecules are oblique to each other. And when you do 400 nanometer light, you're exciting the n to pi star transitions. The n to pi star transitions are weak dipoles, and then they lead to a small excitonic shift. But that's not what's important, because the other thing that happens with these excitations is they actually travel through the lattice. And they travel, the distance they travel is proportional to the intensity of the transition. So what we see is for the n to pi star transition, the excitonic travel is a very short distance because of the weakness of the transition. Whereas for the pi to pi star, it's a very intense transition, and the exciton travels a great distance. So that means that the exciton, the n to pi star, that's 400 nanometers and below, doesn't travel very far. So the excitation isn't sufficient to drive full polymerization, because eventually the energy doesn't get to the molecules. But in the case of the pi to pi star transition, the long range effect of the pi to pi star transition allow formation of high polymer. Mendel-Cohn came up with the idea of the reaction cavity, which is a region of the crystal surrounding the reacting species and the product. I couldn't find a good crystal of Mendel. But anyway, Mendel's work was interesting because what it did was imply mechanical considerations. Because if you think about what a reaction cavity is and how it would control reaction, when you form a product in the crystal, what happens? When the product forms in the crystal, it has to kind of find its home in an environment that it was not made for. And so it must do work against that cavity. So you can think of that cavity as having a surface energy or surface tension. And so you can think of the surface tension of a cavity around the host and the product molecules. Excuse me, not the host, the reacting in the product molecules. Now, another consideration on this is, of course, that how do you calculate that? Well, what does that surface tension really mean on that scale? Well, clearly what it is a measure of is the local steric force, forces of what are called the force constants in the lattice, or the strain field in the lattice. So if you know the strain tensor, you can estimate the stresses that are effective and affecting the reactions and the product. And that leads to the conclusion that when the product grows, it will grow in the direction that's softest in the lattice. Then Mike McBride came up with that idea of steric compression, which is pretty related to the reaction cavity, but a little more specific. It is a force acting at or near the reaction site that influences the atomic motions along the reaction coordinate. Now that sounds suspiciously like the problem we saw before with the polydiacetylene, where they had to find a vibrational mode that allowed the lattice to accommodate the product of the polydiacetylene polymer. So in a sense, McBride is phrasing that as a more general principle. Then finally, my old dear friend, who was a lab mate for 5 years and an office mate with me, Joel Bernstein, came up with the idea, or not the idea, kind of discovered and figured out conformational polymorphism. And this is, of course, where you get a molecular crystal made up of a molecule where the lattice constants can be quite different, or in some cases quite similar. But the main difference is the shape of the molecule, not due to any reaction. And Joel was very instrumental in showing that this is an important aspect of organic solid-state chemistry. Before then, polymers were viewed more as just different packing arrangements of the same molecular shape. But Joel showed that there's also different polymers formed due to conformation. Of course, then the chemistry can change also. And then finally, the work of Peggy Eder, Eder's rules, which everybody I'm sure knows. They're listed in the first table there. These were arrived by Peggy for graph theory analysis in the main. She worked with Joel on this to some degree, but it was mainly Peggy's ideas that came to fruition. And these are important rules of construction for crystals. Because, of course, one problem of organic solid-state chemistry has always and will always be crystallization. How do you crystallize? And how do you drive it? And how do you control it? And Peggy pointed out that hydrogen bond rules are great ways to construct crystals. So this work formed the basis then of crystal engineering, which some of you are reporting on in this conference, and which went to the next generation of workers, such as Desiree Zhu. But the fundamental work was for crystal engineering was Eder's work, hydrogen bonded, and then the work of Kitagoratsky and workers in Leonard Jones potentials. And of course, I avoid kinetic studies done by early physicists that lead to work such as Mike Ward does. Now, Dave Kearns was recognized as such a giant in the field that there was, when he retired, there was a symposium in his honor. Now, Dave was kind of the core of a group of workers that were found in the American Midwest. There was a very large concentration of his students, Paul's students, other students, such as myself, that were working in organic solid-state chemistry in the Midwest. So in his honor, a bunch of us in the Midwest got together and formed the Midwest Organic Solid-State Chemistry Symposium. And it was meant to operate in the off year from ICOS. This is a poster from his retirement, which was the first MOS, which is the way we pronounce it, symposium. Peggy Eder was also involved in MOS. She came up with the idea that MOS should be mainly for students, and when we do have MOS, we heavily limit. Usually there's only one senior speaker, sometimes none, because it's all run for the students. That was Peggy pushed for that very hard. I would point out that there's Mike McBride showed me an interesting series of pages that he kept from his time as a faculty member at Yale. If you look at the list, this is a list of in 1967 of all the postdocs and graduate students in the Yale chemistry department. And in the first slide on the left, if you look, you'll see two names of workers. You'll see Gerhard Wegner, who we talked about with polydiacetylenes, and then we you see Jerry Schaefer, who I have not talked about because he's still alive. In the middle slide is Mr. Bernstein. And then on the far side, you'll find me. And then there was Mike himself, so there were 5 of us there. But except for Joel and me, no one else had any interaction with anyone else as far as we know. And so it was kind of weird that there were 5 people that were going on organic solid-state chemistry. So be aware of what your colleagues are doing, it's important. Okay. I don't like still living in the past, even though I'm from there. And I would bring in the one paper that is from a living being, and that's J.J. Gilman, who came up with this idea of metallization due to pressure. And Gilman is not a chemist, he's an engineer, but he was aware of homo-lumo gaps. And he figured out that pressure could drive a homo-lumo gap to be so small that you would get metallization. Now, if that's the case, we know that we don't need metals to get chemistry going. So pressure can drive reactions. Of course, that's been known for years. But the thing Gilman emphasizes, and later workers are aware of and pushing, is you have to look at crystals as a substance, as a ponderable mechanical substance, and you can control that mechanics, and the chemistry must be related. For example, I've always felt there should be an experiment done, like the Curtin and Paul experiment, where you take a crystal and apply several uniaxial strains to it, or stresses to it, so you generate strains, different strain fields, and then look and see how the reactivity of the crystal is affected, because it would imply that you should be able to control your product yield and maybe even the type of product by the strain field you impose on the crystal. Another possibility in strain is, of course, is to change the strain by introducing defects into the crystal in a known fashion. In fact, the best way to do something like Len McGilvery does, and make coke crystals, and for seeing if you can use that kind of approach to affect the strain tensor of the lattice and change the strain fields from a chemical point of view. So I think I was delighted to see in the program that there are a large number of papers dealing with mechanochemistry, because I do believe that that's a very, very rich field. And don't forget, those strain fields arise because of collective interactions. So I'm still waiting for people to deliberately control the excitonic behavior or the phonon behavior, which are the same argument of transition dipoles instead of electronic dipoles, to drive chemical reactions. So with that, I will end.
Well, thank you very much, Craig. That was really nice. We can take time for a couple of questions. Would that be okay, Mr. Conference Chairman? If anybody has a comment or a question.
I have one question, if I could make.
Sure.
Luca Catalano from the Free University of Brussels. I like your take, maybe. The phone? Yes, easy. Oh, okay. Your take on the phonons, the role of phonons in driving and pushing and assist mechanochemical reactivity or crystal reactivity in general. So I'm wondering, this could be also a way to control polymorphism, So solid to solid crystalline transformations, so from one phase to the other, without covalent rearrangement. So kind of a soft touch to change crystal structures.
Well, I guess one could argue that a phase transition could be viewed as a chemical reaction. And yes, in certain solid state, well, in any solid state transformation, there's something called a phonon soft mode, which is a specific vibrational mode of the molecules in the lattice. So if you could figure out how to oppose that, you would probably be able to stop the transition, have it occur at a higher energy. Whether you could find, and I suppose it's also conceivable, you could apply a pressure or stress in a direction such you weaken the crystal, and that would be the softer mode than the one that leads to a transition that's, say, unperturbed. And so you might drive it to yeah, that's an interesting idea, to a new lattice.
Thank you.
Pancho doesn't have to, but if somebody else has a question, I think what Luca just showed us a great idea. You tell us who you are and where you're coming from.
So I guess I don't have to present myself. Craig, that was a wonderful talk. Thank you so much. I would like to focus on the concept of reaction cavity. I got my PhD in a laboratory where reaction cavity was one of the main motifs, where my professor Yuji Ohashi actually worked a lot on reaction cavity. But somehow that concept evolved in parallel in different laboratories. So we have reaction cavity by Michael McBride, and we have Boldyrev in Russia, and Yuji Ohashi in Japan. Could you make a parallel and tell us more about the differences and overlapping aspects of these three different schools that we're talking about, basically the same thing?
Well, actually, there are three different schools. There's mine. The trouble is with the verbal description of a reaction cavity is it's not precise. There's no way to do it unless you can pin down the physics. So I think that unless you can pin down the physics of what you really mean, it's they overlap enough in their general concept that they have this idea of there's some kind of interaction where you're taking the lattice as a whole, and then you're looking at these reacting molecules, and you're averaging, it's like a dielectric field around a transition dipole that you're averaging, and this average field that's around the reacting molecules is affecting it. But beyond that, there may be different kinds of reaction cavities, but until you can get a more precise definition, I think that's one thing the field has suffered from, is that initially all the concepts that I pointed out here were quite qualitative, but they're good chemistry, because that's the way chemists act and think. We think in generalities, we think in pictures, we think in kind of a groupthink way. But if you really want to deal with solid, you have to go and remember the experts of solids where the physicists still are. And you have to learn enough solid state physics to translate it into something more precise, in my opinion. Of course, I'm biased.
Thank you, Craig. One more question.
Thank you. Can you comment on, I'm Hagai Cohen from the Weizmann Institute, Israel. Can you comment on using polarized light, polarized IR, in order to really excite or enhance?
Yes, it's very important. Crystals are very anisotropic, most of them, and as I put out in the Davidoff experiment, I didn't explain how the experiment is done, but what you do is you take a crystal face. Let's say if you want to take a spectrum off the A and B axes, you go to the 001 face, and you take polarized light along the A-axis and polarized light along the B-axis, you get different spectra. And the same holds for Raman. If you use polarized light in Raman, you will also find a difference. And because in Raman, of course, you're getting changes in polarizability, and those changes in polarizability are tensorial. And so you can do that analysis also with polarized light. In fact, Paras Prasad did that with his photon-assisted studies. So yeah, I think that people don't exploit the anisotropy of crystals enough, and polarized light is one way to do it. For example, one thing that's these fundamental experiments, like the mechanochemical experiments, when people use ball mills to get new products, it's obviously a mechanochemical event, but it's so difficult to deal with the forces involved because you're dealing with all the strain tensors in the crystal. It's better to apply uniaxial stresses to the crystal and see what happens with the chemistry. By the way, of course, there are two types of mechanochemical processes. One is a naive one of thermalization due to the mechanical equivalent of heat, and the conversion of heat into, mechanical energy to heat. That's not very interesting. It was essentially dealt with by David Curtin. But the other interesting one is the direct conversion of mechanical energy into chemical process, into chemical energy. And that was what Gilman was actually talking about. Because when you talk about the Helmholtz-Lumel gap, you're talking about heating, you're talking about electronic states. And again, that could be polarized and followed with polarized light through the electronic spectra.
Okay, so, well, thank you very much. So will you please join me and thank Craig for setting us up to a very thoughtful and exciting start.
So thank you very much for that wonderful introduction. I guess it's a real pleasure to introduce Professor Aurora Cruz Cabeza, who is, of course, known to all of us. She's a real interdisciplinary researcher doing computational chemistry as well as crystallography, and I think she'll be touching on that later on today. Professor Aurora is currently reader in crystallization research at the University of Manchester. And the interdisciplinary work that she's currently engaged in, I guess, started way back in her training. Aurora did a master's in heterogeneous catalysis in the University of Cordoba. She then followed this up with a few months at the Royal Institution, and that got her interested in computational modeling. Aurora then went on to do a PhD with Professor Graham Day and Bill Jones. And in 2008, she earned a PhD in physical chemistry. Since then, she has worked in various positions, including in the pharmaceutical industry, where she's worked in Pfizer and Roche, Some of the best known work that Aurora has done is in polymorphism, working with both Susan Royce-Edens as well as the late Professor Joel Bernstein. Aurora has also worked at the University of Amsterdam and also at the CCDC. So that gives you a flavor of the kind of work she's been doing both in polymorphism as well as computational modeling. In 2016, she joined the University of Manchester, where she's now a reader. She has over 75 research papers, 60 invited talks, and today we're very excited to welcome her here and hopefully to talk to us a little bit about the difficulties of conformational modeling and also how that affects both crystallization and also crystal structure prediction work. So with that, I'd like to introduce Aurora to the stage.
Click now? Yeah, very good. Thank you for the kind presentation, Jean-Marc. And Panche, I hope I still count as the young speakers in your diversity count. Though I'm not sure anymore. It's been so difficult to organize conferences in the last few years. So I thought of Panche, how it's been so complicated and you had to cancel and reorganize again. So I thought about the flexibility problem in crystals because it's like untwisting something that's really twisted and it's just really difficult. So I thought today I wanted to give an overview of why I think it's still a very challenging problem, which is dealing with molecular flexibility in the solid state and crystallization. So first of all, I don't think I need to say much about the importance of molecular conformation. Conformation is important in biology, in protein-ligand interactions. We can design molecular switches that change conformation upon irradiation of light. Some disease may be directed by the way proteins assemble into specific conformations. Maybe you know about these molecular machines, molecular rotors, molecular cars. And of course, molecular conformation is also important for crystals, and this is what we really care about in this community. Now, how flexible are molecules that we work with? So it depends. If you're an academic, probably your answer is not very much. My molecules are really simple. So if you look at academic work, it's typically glycine, benzene, or things that have one rotatable bond or something simple. But if you're in industry, you probably think that your molecules are really complicated and have 1 million rotatable bonds. So this is, for example, ritonavir, which is a very complex drug compound that has 22 rotatable bonds. So actually, this is a very nice paper that was published in 2019, where there was an analysis of the structure of molecules in the CSD, all organics in green. And you can see that in the CSD, it's quite biased with molecules that don't have any rotatable bonds. And there is distribution as well, but if you look at molecules that drug companies have to work with, like in AstraZeneca or Pfizer, you see that then they're much more complex and they're much more flexible. And these are examples of some pharmaceutical compounds. They're the most best sold drugs in the market, and they can be really complex with lots of flexible rotatable bonds. Pesticides, even in the food industry, you will find molecular flexibility everywhere. And from the same paper by Bryant in JPharmSci in 2019, you see that it is a trend through the years, the drug compounds that are being approved are becoming more and more complex with more and more flexibility. So when molecules are flexible, then they can change their shape by virtue of rotating their bonds. So in the gas phase or in solution, they may exist in different stable conformations, different conformers. They may interconvert between them. And when you push those molecules into the solid state, then some of those conformations make it into the crystals, but some others don't, and some others make it if they include solvents, for example. And we don't know very much what is happening with this molecular flexibility during crystallization. And this is an important problem. And is there a link between what you see in solution and the conformation variability in the gas phase and what you see in the solid state? And as you increase the number of rotatable bonds in a molecule, the number of possible shapes your molecule can have, the possible conformers, really increases exponentially. So a molecule, typical molecules that drug companies have to deal with might have between 6, 7, 8 rotatable bonds, and that could potentially make up to over 6,000 conformers that are stable, so they are interconverting between them. So the problem scales up really quickly, and as we have to deal with more and more complex systems, then this is becoming more challenging and more important. So there are different challenges that flexibility brings to the scene. First, there are challenges regarding the solid state. So you might encounter conformational polymorphism or a conformational change through solvation. There are challenges in the modeling because it's more difficult to sample the space when you do, for example, crystal structure prediction, or it's very difficult to model accurately. And there are also challenges in crystallization, because often it's being reported that flexible compounds are harder to crystallize. So in terms of solid state, for example, we know that when we see changes in conformation, that might impact crystal properties more. So, for example, these are the Roy polymorphs, and there is a strong link between the color of the polymorphs and the conformation. When you look at solubility changes, this sample of ritonavir, there was a very dramatic change in conformation between the two polymorphs. And that was related to a significant change in lattice stability that impacted the solubility of the drug significantly. But we also did some modeling of conformational polymorphs and polymorphs in the past, and we realized that conformational polymorphs in blue have the potential to differ more significantly in the stability. Somehow, if you're able to lock different conformers in different crystal structure, there might be more major differences in properties. And in fact, if you look at drug product recalls due to polymorphism, you will realize that they're all conformational polymorphs. Ritonavir, 1998, had to be removed from the market and reformulated. It's a conformational polymorph. Mebendazole, 1999, same story, conformational polymorph. Rotigotine, 2008, same story, conformational polymorph. So if we really want to control those issues, we really need to understand what's going on with conformational changes and how to control them. This molecular flexibility is also challenging when it comes to modeling, because if you think of a molecule as a shape, you can pack a specific shape in thousands of different ways in 3 dimensions. But if you now change the shape, you have that new shape can also be packed in 1,000 different possible ways. So as you increase the number of conformers, each conformer will give you different stable packings. So the problem of crystal structure prediction can become really complex. And it's also challenging to get the energy rights when you're doing modeling, when you have conformational polymorphs. This is a nice paper, early paper from 2008. I can't see it from here. 2008, that's right. And you will recognize many of these names here, some important people in the modeling world, including Sally Price Graham, who's here. And they looked into the modeling of the interplay between intra and intermolecular interactions, especially in conformational polymorphs. when you had changes in hydrogen bonding. And they realized, I can't read it from here, that the predicted stability differences between them due to this modeling were unreasonable. They were really unrealistic, quite large. And part of it was because if you compute the electron density in the gas phase to do your modeling, that's going to be bring significant errors later. And they observed that the biggest differences occur in polymorphs where you had a very different intramolecular hydrogen bonding. So, and finally, when you're doing crystallization, which is also very important to this community, molecular flexibility can also be a problem. This is one of my favorite papers of all time, actually. It's Lian Yu, Susan and Christine, Susan Reitzel and Christine Mitchell. It's a beautiful paper. I recommend the young students to read it. But they pointed out here that the reduction of crystallization tendency for conformationally flexible molecule arises from the presence of multiple conformers in the crystallizing media. So the more flexible your molecule is, typically will also mean that the system is harder to crystallize. And if you look at one of the main key paper on the ritonavir conformational polymorphism, you will also realize the authors talk about the difficulty of the conformational change in going from the conformation of form 1 and form 2. And therefore, if there is a big energy barrier for interconverting some conformers, this may give you a problem in crystallization. And another really nice piece of work is from Wicker and collaborators in Christian.com, where they look at this concept of crystallizability and will a molecule crystallize. So they took a lot of data from the CSD and from commercial providers, and they wanted to understand what made the molecule harder to crystallize. And perhaps to no surprise, is the number of rotatable bonds came as one of the key parameters in this problem. So if molecules that didn't crystallize, were in red, tended to be more flexible than molecules that for which you had crystal structures in the database. So I hope you agree with me now after this short introduction that molecular flexibility, it really is a problem that we should look into in this community. So I'm now going to take you through 7 different points and reflections a little bit more deeply, and then I'll conclude my talk after those. So the first reflection is on how it is important to have good definitions in doing science. And 2 concepts that really helped me understand the issue of molecular flexibility was the concept of conformational change and adjustment. And this was some work that I did with Joel Bernstein. But let me tell you a little bit more before about conformations in the gas phase and conformation in crystals. Conformations in the gas phase are dictated by intramolecular forces only. So you only have the pulse of the intramolecular forces. But as soon as you put your molecule in a crystal, you have intramolecular forces and intermolecular forces. It's getting that balance right that is really important. But actually, the gas phase conformational energy is very useful, and we should use that to try and understand the phenomena that we see in crystals too. And if you go to the IUPAC and you look at the definition of conformation and conformer, you will find that a conformation is really any arrangement of a molecule in 3D. So if you have a molecule in one arrangement and you change 1 degree of that arrangement in 1 torsion angle, you will generate a new conformation. So any changes will generate a new conformation. But a conformer is a conformation that is at equilibrium, right? So it's a conformer is a stable conformation. So it's a conformation at equilibrium in the gas phase, for example. So using the gas phase potential energy surface with Joel Bernstein, we were thinking about the concept of conformational polymorphism. And these definitions really helped us understand and classify the problems and classify polymorphism. So conformers are those conformations sitting at the energy minimum, and so we can use the gas potential energy surface to find those conformers. And of course, as soon as you put one of those conformers in a crystal, it's going to distort slightly due to the intermolecular forces. So we call this phenomenon conformational adjustment. Some other scientists call it strain, conformational strain. So you deviate the geometry slightly from the minimum in the gas phase due to the intermolecular interactions. But to generate another conformer, you need conformational change. You really need to go above an energy barrier. And that's important because different conformers might not be available in solution, for example, or in the gas phase. So differentiating these two concepts is important if we want to understand molecular flexibility in the solid state. So once we came up with this definition, it was much easier to classify polymorphism because you only have packing polymorphs, if you wish, for polymorphs which conformations are related by conformational adjustment only. But you will need conformational change to have conformational polymorphs. And let me give you a practical example. So here we have ROY, which is one very important polymorphic compound. And these are 7 polymers of ROY that have been determined, for which we have crystal structures. If you just look at the value of the torsion angle of this rotatable bond, it will be very difficult for us to say anything about which of those are conformational polymorphs. But if you generate a potential energy surface now, and plot the conformations of these different polymorphs in there, then very easily we can see that we have 2 conformers in these 7 different polymers. So, and in fact, the conformers, the conformations that lie around this conformer tend to produce red polymorphs, and the conformations that lie around this energy well produce yellow polymers. So here we see a very dramatic change in the color. And actually, if maybe you're not a theoretical chemist, so you don't know how to generate these potential energy surfaces, so you can actually use the CST to tell us about this energy. And in fact, the distributions of torsion angles in the CST tend to mirror really well the gas phase potential energy surface, which means these molecules are slightly distorted around their gas phase conformer geometries, just slightly distorted, and these distributions marry very well with the potential energy surface. So just by looking at the CST distributions, you should be able to identify whether a molecule has conformational change. But we also did a lot of energy calculations, and we did some overlays of structures, molecular structures, and we came up with some rules that will help us identify conformational change very easily. So if one torsion angle changes by 95 degrees or more, it's for sure you have conformational change. But if you overlay 2 molecules using some algorithms in Mercury, and this value is more than 0.375 on atomic positions, mean square deviation of atomic positions, is 90% chances that will lead to a conformational change. So these are useful rule of thumbs that can help us identify conformational change and therefore conformational polymorphism. Now, what about conformations at the top of the energy barrier? What do we do with those? Well, do they even exist? And actually they do. So this is biphenyl, and biphenyl may adopt a completely planar conformation or a twisted conformation. And this is the distribution in the CST. So according to the distribution, maybe you think there is a minimum there. But if you do a potential energy surface in the gas phase, you realize that actually there's a maximum there. And there's an energy penalty of 8 kilojoules per mole for biphenyl to adopt that geometry. So what is biphenyl doing at the top of an energy barrier? So this is when definitions can become complicated. But actually, even though this bar plot is really big here, it's only big because there's a lot of observations with that torsion angle just exactly 0. But if you actually integrate these bands, you'll see that the the planar conformation is not the major. The twisted conformation is the major conformation that you see in the database. But if you now take this distribution of observations from the Cambridge Structural Database and split it into crystal structures with Z prime equal 1 or greater, and Z prime equals a half, then this distribution splits really nicely into 2. So it turns out that all of these observations where this rotatable bond is 0 and biphenyl is planar, the crystal structures are Z prime a half, so biphenyl is sitting precisely on an inversion center, typically. And why is that important? Why should we care about that? Well, actually, what we did, we took biphenyl and we slowly rotated biphenyl from 0 to 100 to 90 degrees, and we did crystal structure prediction and calculated what's the stable packing for this specific conformation systematically. So if you do that, so you have your intramolecular energy in blue and your intermolecular energy in orange, and then you suddenly see that when the molecule sits in the inversion center, the intermolecular energy is really optimized. And biphenyl is really able to maximize these aromatic interactions. So if you now add these two together, you have a potential energy surface of the crystal where you have a minimum that's driven by the intermolecular energy and a minimum that's driven by the intramolecular energy. And so this is really nice, but this is really useful to know, because if you're doing crystal structure prediction, maybe you should think, well, can my molecule sit in an inversion center? And if it can, maybe you should consider those conformations at the transition states, because they could generate packings and intermolecular interactions that are really optimized. So that's my point number 1. Point number 2 I wanted to talk about is a little bit more on conformational polymorphism and conformational Sony pairs. What are Sony pairs? There's nothing fancy or electronic. It's just, we call Sony pairs solvate and neat form pairs. I'll talk about them in a minute. So once we can define the phenomenon of conformational polymorphism with our definitions clearly, then we can go on and look at the database, the Cambridge Structural Database, to look at what is the distribution of polymorphs and conformational polymorphs out there. And this is, I'm just going to remind you, these studies from 2014. But if you analyze the entire database in 2014, you will get about almost 1,300 families of polymorphs. And then you can classify them depending on how many polymorphic crystal structures they have and how many conformers are involved in those polymorphs. And this is the distribution. So you can see that about 90% of families only have 2 polymorphs, and just 10%, a bit more than 10%, will have 3 or more polymorphs. And typically, the vast majority, well, about 63% will only have 1 conformer, but then you have 2, 3, 4, even 5 conformers. So what are, in total, is about 36% of polymorphic molecules in the Cambridge Structural Database show conformational polymorphism. 36%, yeah? And what are these nice extreme examples of polymorphism? So we have chloropropamide. It's our most conformationally flexible with most conformer polymorphic system in the database, with 6 polymers and 5 conformers, and ROY with 7 polymorphs and 2 different conformers. And remember, this was 2014. If you keep looking, you find even more. And actually, nowadays, I think there are 12 polymorphs of ROY, which keep being amazing. I mean, how this very simple compound is able to make so many polymorphs, it's mind-blowing, I think. But most interestingly, I think, if you look, the database may be biased towards some specific type of molecules, and we talked about this at the beginning. So we academics are biased towards simple, rigid compounds. So if you actually show the distribution of conformational polymorphism as a function of number of rotatable bonds in your molecule, you clearly see that as you increase the molecular flexibility, if your system is polymorphic, then conformational polymorphism is going to be even more prevalent. So if you have 8 rotatable bonds, 80% chances are that your system will be, if it is polymorphic, it will have a change of conformation in its polymorphs. And with my students at right, we looked at conformational SONI pairs. What's a SONI pair? It's a solvate and a neat form pair. So you have a molecule that crystallizes as a solvate, like this is, for example, morphine, crystallizing as a hydrate, and then also as a neat form without any solvent in the crystal structure. So we looked in the Cambridge Structure database and we retrieved about 1,500 SONI pairs, and then we were interested to look whether these conformational effects change when you have a solvent included in it. So then we looked at different distribution, different type of solvates, and we looked at the SONI pairs and we looked whether or not there was a conformational change between the system being solvated and the system being unsolvated. And we looked at different types of solvates, and the numbers changed slightly, but the overall is that 46% of those pairs will show a change in conformation. But so does that mean solvating will change the conformation more than changing polymorph? Actually, no. If you then break out the data into the probability of conformational change with number of rotatable bonds, then you see that the trends are very similar to the trends in polymorphs. But it's just that we have more data of larger molecules and more flexible molecules when we look at our solvate data sets. And you can then, we calculated what are the energy differences between these conformers. And typically, energy differences are less than 20 kilojoules per mole, typically. But there are some exceptions that are larger than that, but very few cases. And the majority of actually these conformers that you see in different polymers and different solvates tend to be very similar in energy. And we also found that if instead of just computing just the conformational energies, you compute the conformational free energies, then these bands squish even more, so the energy differences are even smaller. And also if you add solvent effects. And this work was actually a very nice agreement with some work of Graham Day and Hugh Thompson that they did. They published this paper at a similar time as Joel and I had the conformation polymorphism paper. And I highlight there that some molecules are distorted by up to 20 kilojoules per mole when it comes to different conformers crystallizing in crystals. So energies tend to be small, but actually this work is different to what we did in the fact that Graham looked at generating different conformers that are possible for the flexible molecules and looking at the stability of the conformer that you see in the crystal structure. And often, the higher energy conformers are seen because they're more extended. So through being more extended, although they're less stable in their intramolecular energy, then they're able to generate more intermolecular interactions, therefore being a preferred conformer in the solid state. So, and what we also saw is that in our conformational polymorphism papers that not all rotatable bonds behave the same way. So we derived some statistics, and I'm not going to go through this table in detail, but if you have an amide group attached to an alkyl chain, this bond tends to change conformation in 27% of times. So it's quite prone to changing conformation in different crystals. However, if you look at alkyl chains on their own with no other, this bond in the middle of the alkyl chain doesn't change very often, only 6% of cases. So it's something about the torsion angles that we look at or the environment around those rotatable bonds that will make them more prone to change than others. And if you look at conformational adjustment, it's the same story. So alkyl chains hardly go away from their gas phase minimum. But if you look at really bulky, weird-shaped rotatable bonds, they often distort by much more. So these are my reflections related to conformational polymorphism and conformational Sony bears. What about modeling conformational flexibility? Well, Graham is making faces. I know you know Graham, exactly. So I learned this very early in my career, my first paper, right, Graham? So I was looking at doing crystal structure prediction of carbamazepine. And Graham had used this method to predict 80 compounds, I don't know, a lot. You had a paper with 30 or something like that, a lot. And the method was working really well. And I go on carbamazepine, and the method didn't work. And I thought, Graham, I did something wrong. Something I did wrong, and I don't know what. So I kept thinking why I didn't predict. What is this structurally a polymorph? Is there something I'm missing? So after thinking a long time, and we realized that the amide groups, when you have nitrogen in your molecule, is really complicated to do the modeling. So at this time, this was 2006, we used to use DFT or quantum mechanics to model the intramolecular part of the crystal, and we used to use some classical models, force fields, to model the intermolecular part of the crystal. And so we realized that there was a small geometry change around this nitrogen where just the hybridization was changing slightly, and it will pyramidalize one way or another, and those hydrogen atoms will move just ever so slightly. So we decided to try and model that. So when we put that into our model then, we came up with a much better energy landscape for our system, and we predicted two of the polymorphs to be the most stable. So this shows how even the small flexibility problems, just a small deviation of a proton position, could have a huge impact on the final, on your modeling. I won't talk about Form 2 or 1 because they're complex, and there's a whole lot of the story, and I could spend a whole hour talking about them. But this was I was very proud of this landscape because introducing this effect was very difficult at the time. A few years later, the whole field really changed. And because DFT does really poorly at modeling dispersion interactions. So if you were doing quantum mechanics to try and model crystals, it just wouldn't work because dispersion interactions are just not well modeled. But in 2008, around that time, there was a lot of development of models of DFT with dispersion-corrected DFT. And I think that really changed the field, because if you used full periodic DFT methods, you optimize your intramolecular energy and intermolecular energy at the same time. So this is a very nice paper because it was the first time that the force systems in a crystal structure prediction blindness were predicted, and the use of DFT was a major advance because it really changed the game, I think, because force fields didn't have the right accuracy to do the modeling. But that's not the end of the story. Some years later, we have some work by Alexander Tkachenko, where they realized that dispersion corrections needed to be improved even further. So he went on to develop some many-body dispersion interactions, way of modeling that for molecular crystals, and that showed to be very important. But 2019, we still can't model conformational polymorphs. This is another fantastic paper where Jonas Neiman, Lien Yu, and Susan Retzelidens, they tried to predict the polymorphs of Roy. So we've talked about Roy already. And big challenge. So you try and predict them, you think, well, since this is a small molecule, it's only one torsion angle, why? Or there's another one here, but it's kind of restricted by the hydrogen bonding. Surely we can do this. And if you generate your landscape, and then lots of the polymers have very strange energies of 8 to 10 kilojoules per mole and higher. And the authors noted that modeling electron delocalization was a real challenge. And again, we come back, well, this is actually really difficult for conformational polymers. So in more recent times, Greg Barron has been doing an amazing job at trying to sort this out. So he's been applying molar pressure MP2 method with dispersion to model the intramolecular part of the DFTD modeling of the crystals. It's getting complicated. But if you just look at the potential energy surface in the gas phase of just this molecule by rotating this bond, this is modeled by DFT in purple. And if you use better models that are able to describe electron correlation better, like MP2 methods or copper cluster methods, then you realize that this energy profile looks extremely different. This is an energy difference of 4 kilojoules per mole just for the intramolecular energy. So he went back to look at ROI, and if you just model ROI with DFTD, it won't work. But if you now take the intramolecular energy and use MP2D methods for that part only, and you plug DFT for the red, then the prediction is just fantastic. Now you can see how your conformational polymers are coming out as the lower energy crystal structures. But you know, this is not the end of it. There's still a challenge. And in fact, I had the pleasure to work with Greg, also with my student Sarah, where we looked at this interplay between the intra and intermolecular energy errors in the modeling of conformational polymers. And we realized that we looked at the errors, the red bars relate to the intermolecular energies, the intramolecular energy in red, intermolecular energy in blue. And you can see that the DFT methods often overstabilize the intermolecular energy. Sorry, the other way around, I can't see it. But what I wanted to say here is that the intramolecular energy errors and the intermolecular energy errors sometimes balance out when you use DFTD only. So, and this is what we see here. And they get minimized when you use MP2D methods. But it's still a lot we need to do to be able to know when these errors cancel and when they don't, and how will my conformational polymers be correctly predicted with these models. Still a challenge for the students, for the future. So another topic I was very interested in, well, is changes in conformation from well, I've already talked about this a little bit, but I wanted to go more specifically on this topic, also from an experimental point of view. Changes in conformation from a neat form to a hydrate, and what are the implications of those conformational changes. So with my student, Pat Basford, we looked at this molecule, fluconazole, which is an antifungal drug commercialized by Pfizer for many years back. And there are many polymers for this system, but there are 3 main anhydrous polymers, which is anhydrous B, A, and C. And this is the order of stability, being more stable in A and C. And there is one known hydrate. So if you do some thermodynamic studies, you will find out your critical water activity, above which your hydrate will be the most thermodynamically stable form, and below which your anhydrous form will be the most thermodynamically stable form. So we crystallized the 3 anhydrous forms, and then we studied the hydration behavior of anhydrous form A, B, and C. So if you expose your samples to 54% relative humidity, nothing happens. For nearly 280 days, nothing happens. But if you increase the relative humidity to 75%, then you start to see that anhydrous C starts hydrating quite fast. That's the fastest in kinetics of hydration. Then it's anhydrous A, and then it's anhydrous B hardly hydrates at all. So here, the three polymers show different kinetics of hydration. So the crystal structure really matters when it comes to transformations between anhydrous forms and hydrates. And this is the order of stability. B is more stable than A, and then C. So the kinetics also follow the order of stability. But what we also found very interesting is the impact of conformation. Because if you look, this is the conformation that you find in the monohydrates. This is the conformation in the anhydrous A and C. As you can see, the main difference is that the hydroxyl group has rotated away into this area. That's the main difference, the rotation of hydroxyl group. But if you look at anhydrous form B, there are two independent molecules in the asymmetric unit, and there are significant rearrangements of the conformation. And then you can model the conformational energy barriers of this, and it's very facile to go to just rotate one hydroxyl group. So if the molecules, if water is able to penetrate somehow the polymorph, or at least interact with the different surfaces of your sample, it might be an easier conversion onto the monohydrate because they share the same conformation. And then we look to the reverse process. What if we look at the hydrate? What happens if you have the hydrate and then you heat it up, and eventually you see dehydration around 78 Celsius? And so we did some modeling of this as well. And we realized that as you heat your simulation cell, it expands a bit. And then eventually, as you keep heating, then you see the hydroxyl group rotating away from the monohydrate conformation to the anhydrous C conformation. And when 50% of the hydroxyl groups have changed conformation through this facile rotation with hydroxyl group, then you start to see diffusivity of the water within this simulation box. So that's, again, a very nice example how just a small conformational change event of this hydroxyl group rotation initiates the whole dehydration process. So I thought it was a very nice story. Now, conformations and crystals in action. I think there was some Nobel Prize Croatian that said a crystal is a chemical cemetery. And I think, well, but this community knows that this couldn't be more far from the truth. In fact, crystals can be a lot of fun, very dynamic, and it can be in action. And the first paper that came to my mind is this lovely work by Keiichiro Ogawa and Jun Harada. And Keiichiro organized the ICOS some years back. And he's so much fun because he also sings opera. So I love meeting Keiichiro in meetings because he will always sing me an aria once we talk about science. And he wrote this amazing paper that really inspired me as a student. It's called Pedal Motion in Crystals. So if you have azobenzene, right, you have two rotatable bonds. If you were to rotate one and not the other, because those molecules are in a crystal, it just wouldn't work. But if you rotate both at the same time, then you can generate what he called the pedal motion in crystals. So it's like riding a bicycle on a molecule in a crystal. I think it's fantastic. And this is, of course, a change in conformation. And as you increase the temperature, then this motion will start. And when you cool the crystal down, it will stop. And then you can determine by X-ray diffraction the different, you can see both conformers in the crystal. This is a lot of fun. And of course, we have Miguel here, who's going to give us a fantastic lecture. But who thought of molecular machines, on surfaces are quite complex, but you can crystallize them. And if you crystallize molecular machines, and in this case, molecular gyroscopes, then you can control how they're aligned, and you can then get some control of the solid state dynamics and the function of your crystals. And I think Miguel is going to tell us about it in a talk during the meeting. And of course, you may also be aware of the phenomenon of jumping crystals, who was first discovered by Peggy Etter. And Joel Bernstein wrote a fantastic paper about it, and Panche took these effects into the next level. He really was able to understand what was going on. And this is an example of a jumping crystal that Panche worked on, where just you heat in the crystal and eventually it jumps, and there is a phase transformation normally when you see these crystals jump. And in this case, the crystal goes from form 1 to form 4. And you can see the crystal shrinks massively. It's really impressive. And then if you cool down, the crystal expands again, because these are reversible phase transitions. But if you look at the molecular level, it turns out that in this case, it's driven by conformational change, where you have this molecule that on heating closes like this. It's like a molecular tweezer that closes, and that cooperative close through the phase transition makes this huge change in the crystal structure. There's rings and the crystal jumps. I think it's really cool effect. So also, in crystalline actions, we need to think about molecular conformation. So next is another area I'm really interested about, which is about solution. No? So we've talked about gas phase conformers and crystal conformations, but what happens in solution? What's going on in that solution? And is there a link between the conformers we see in solution and the outcomes of crystallization? And I think for this, looking at conformational polymers are the ideal systems, because you could change the conditions of crystallization and see maybe if I change my conformers, I will get a different polymer. And there's a lot of really nice work that's been done by Matteo Salvalaglio in terms of simulations, because it's quite difficult to monitor this in solution. And he's done some work on succinic acid with molecular dynamics using some complex sampling techniques where he can get the free energies of these conformers. And then he can work out what are the populations. So this big circle means it's a big population in solution, and these small circles, it's like these are less populated conformers in solution. And you can see that there is a big distribution. There is a dominant one that's a slightly twisted conformer of succinic acid, and then is the linear succinic acid here. And these are the two that you see in the crystal structures. But actually, this is the one, the linear conformer is the one that you see most of the times. And this is the one that makes the stable form. And if you crystallize succinic acid, 99.9999% of times, you will get the crystal with this linear conformer. And there was, in one occasion, for this paper, and I don't know if someone else has reproduced it, there was a rare polymorph obtained with this populated conformer. So really, in this case, we could improve the links between the conformer in solution and the conformer in the solid state, because the dominant conformer in the solid state is not the conformer that you see in solution. And he's also done some really elegant work on ibuprofen, where he looked at how the conformational energy changes in different environments. So you could look at these conformers in solution and generate your potential energy, or when they're absorbed. And so this is quite similar, but when you then include your molecule to the surface and the solid, then it becomes quite restricted. So let me show this plot in a different way. So there are 6 main conformers, and there are 4 of them are well populated in solution, which is the purple color, similarly populated in solution. And then if you go to adsorbed molecule on the surfaces, they're all also similarly populated. But as soon as you go onto the surface or the solid, is the crystal conformer that becomes really the most stable. So the selectivity, at what time do we select the conformation during crystal growth? That's the key question. So here we see a big jump between solution conformer population, adsorbed population, and surface and solid population of the conformer. But at which point does the molecule adjust, and does that matter to crystallization? And of course, if you're looking at conformation in solution, you must look at NMR, and there's a lot of work done in this direction, but I'm not going to discuss this topic today because, again, this would be like opening a can of worms, and I could be talking here for hours. But this is a really nice paper about conformation in solution and in the solid state on tolfenamic acid led by Helen Blade, which I recommend if you want to read about it. And my final topic for today, it's conformation, flexibility, and crystallization. So in Manchester, I did my work on conformation of polymorphism with Joel before arriving in Manchester, but at Manchester, I've been doing more work on crystallization. So how can we understand what is the impact of molecular flexibility when you come into the crystallization? And what's all this business about crystallizability? So if you may have heard this term, crystallizability. What is crystallizability, and how can we measure crystallization tendency in different compounds? Well, it depends on what you're trying to answer. Maybe if you have polymorphs that crystallize with different conformers, you could think about maybe, well, if one of them is more elusive than the other, maybe we could try and think about that. But obviously, you also have the thermodynamic factors impacting this. So it's very complicated to break it down. If you look at different compounds, how can we say which one has a better crystallization tendency? So maybe if there are compounds that you have no crystal structure, you say they're less crystallizable. But what does that mean? And how can we compare how crystallizable these different compounds are? So we think we could do better than just using ill-defined terms. Maybe we could just look at nucleation kinetics, right? You just look how fast does it take, how quickly does a molecule make it into a crystal. And if you can get nucleation kinetics data, then that is a much better defined term to look into this problem. So we were interested in molecular flexibility and crystallization, so we picked these two compounds. There are two benzoic acid compounds with para-substituted with two alkyl chains. This is piboba with an oxygen here, and this is pipentyl with just an alkyl chain. And it's got quite a few rotatable bonds. Piboba can exist in 54 different conformers, pipentyl in 81 different conformers. So we looked at these systems because also if you look at their crystal structures, you see different conformers also in different polymers and also within the same crystal structure. But these conformers, because they are very similar in energy, they just differ in less than 2 kilojoules per mole. And they only differ in the orientation of this alkyl chain. So if you then generate the potential energy surface in the gas phase, you can calculate what's the energy barrier to go from a twisted alkyl chain to a linear alkyne chain. And this energy barrier, it's between 10 and 14 kilojoules per mole, depending on the two molecules, but around 10, 14 kilojoules per mole. And that is consistent with typical alkane rotations, and those have been studied many, many times. So just keep that number in mind. 10, 14 kilojoules per mole is the energy barrier to twist that chain from twisted to linear. So, of course, if we want to understand that, we need to look at rigid compounds too. So, in fact, first we looked at rigid compounds, and we looked at these 4 benzoic acids, and we measure nucleation rates. And using the nucleation rates, then we were able to rank these molecules into which are the faster nucleators and which are the slower nucleators. And this is our order. This is para-toluic acid, PTA. It's the fastest nucleator. And PABA, para-aminobenzoic acid, is the second faster. Then para-nitrobenzoic acid, and lastly, benzoic acid. And we couldn't really understand at the beginning why this order. And I'm going to tell you the reason later. But what about our flexible compounds? Where in this range of how fast nucleators they are, where do they fall? And what does it mean in terms of flexibility? And you would think, well, if these flexible compounds exist in solution, in all these different conformers, 54 for one, 81 for the other, maybe that slows down the kinetics, right? So this could be a hypothesis that we wanted to test. So when we looked at the nucleation rates of these systems, these are just for your, to help you classify them. The flexible compounds are being highlighted in green and the rigid compounds in red. This is the data we got. This is the nucleation rate as a function of supersaturation. And just to give you the order, pentyl turned to be the faster nucleator of all of them, and benzoic acid the slowest. So that was surprising. So it doesn't seem to be having an impact. And when we looked in IPA, that was in toluene, and in IPA we saw similar results. In PBOBA, the flexible compound was the faster nucleator, faster than the rigid compounds. So what we did next is, well, let's do these measurements at a different temperature. So if you do the rates at 2 temperatures, then you could do an Arrhenius plot, and you can calculate the activation energy for your nucleation kinetics. And when you calculate the activation energies for your nucleation kinetics for these flexible compounds, you realize that the activation energy is 74 kilojoule per mole. That's what we obtained from this experiment. 74 kilojoules per mole. That is a lot higher than 10 kilojoules per mole of the conformational energy barrier, if you remember. So because it's a lot higher, the energy barrier for nucleation is a lot higher than the energy barrier for conformational change, then this cannot be your kinetic controlling step, right? So in this case, these conformational effects are unlikely to impact the kinetics. But this might not be the case for all conformational compounds, because actually in ritonavir, the conformational change in ritonavir is far more significant. It's around 100 kilojoules per mole. So maybe in more complex molecules where the energy barriers of conformational change are higher, then there is difference and they become significant. But what we found was important. It was the strength of the aromatic stacking. And the strength of the aromatic stacking was controlling indeed the kinetics of nucleation. So you see that all of these systems will form really nice stacks or aromatic interactions as continuous interaction in the crystal. So when you compute the dimerization energy of these acids in the crystal with regard to the stacking, we saw that the faster nucleators had more stabilizing aromatic stacking, whereas the slower nucleator had less stabilizing aromatic stacking. And actually adding substituents to that ring might go in favor of a stronger stacking. Therefore, our flexible molecules were generally having stronger stacks and being faster nucleators. This is the end of my talk. I've got some conclusions. This is a challenging business. Conclusions are, depending on who you are, if you're an academic or an industrialist. If you're an academic, my conclusion is don't. Forget it. Don't do molecular flexibility. I'm not joking, so you don't need to laugh. And if you're an industrialist, good luck. Now, my real conclusion from the students of the future, untwisting the twisted, this is a fascinating problem, and we need all sorts of expertise to crack it. So please help us in the future. Thank you. This is a photo of my amazing collaborators, my group, Joel Bernstein and Roger Davey, with whom I've done some fantastic work, and I'm indebted to them. and lots of people that have really helped me through my years, the funders. And I highlight Matteo because he gave me some of the slides for the part of the talk, and Kim and Pat because of the work they've highlighted, as well as Sarah.
Okay, so thank you very much, Aurora. So I think we've got a few minutes for questions. So I'd just like to remind people to, if you can just say your name and your affiliation before you ask your question. There'll be microphones, I think, that are going to come around, so let's have them. So we've got one over there. I would also like to encourage students to please ask your questions.
Hi, I'm Hema from Weizmann Institute of Science. It's a very informative talk. But I have one question regarding this link between solution conformer and solids, crystal. So my question is, you have mentioned briefly about NMR. So what we see usually, NMR is like, in solution state, there will be high dynamics unless there is some intramolecular interaction. So what we see is kind of averaged out peaks. And it may not be the same what we may see mostly in crystal because of that. So can you comment on any possible experimental techniques you can think of that have future in this?
You're the future, not me. NMR is being shown to, so that it's complicated to break down your NMR signal into population of conformers, but there's some people doing that work, and Charlie Wand is one of them. And you need to combine simulations with the experimental data on NMR, but it is really difficult. That's one of the problems, because even if you can see the conformers in solution through NMR, you can't see nucleation. They're going to struggle with that, because we struggle seeing nucleation because it's a rare event, and you can't focus, it happens in very localized areas, so which techniques, so we're going to have to improve the techniques that help us see nucleation and help us see conformation at the same time to be able to determine at which point the conformation gets determined. So maybe we're stuck with molecular simulations for now, but we've talked about modeling conformations and how difficult that is. So take that with a pinch of salt also, because our energies might not be right.
Hi, Rod. I enjoyed your talk. Len McGilvery, University of Iowa. So you mentioned that you did I'm going back to the biphenyl situation. So you did the crystal structure predictions based on changing the rotation of the biphenyl up to 90 degrees. And then you mentioned that it's the conformation that holds the center of inversion that eventually allows you to optimize the interactions in the crystal. So I was wondering, that you could try the same approach with an unsymmetrical biphenyl and do the calculation, and then if you did that, I'm wondering what would be the outcome. So an unsymmetrical biphenyl can't hold a center of inversion, of course. And so I wonder what the outcome in terms of the energy situation would look like. It's a very simple thought, but it seems like it'd be interesting to look at.
It's an excellent suggestion, thank you. What I can say is that, so that data that I showed there is just a general look at biphenyls with any substituents around. So you see that's your CSD data, and the simulation data was just simple biphenyl because it's the simplest case. But we do see, and I remember seeing this very clearly, and I think we mentioned it in the paper, in some of the biphenyls you see conformational polymers that have both the twisted conformer and the planar conformer. But yeah, it will be a very nice thing to do, to check whether these maximization of the intermolecular interaction is only due to the inversion symmetry or not, or is just a geometrical effect due to the stacking. It's a great suggestion.
I have the microphone. So Miguel Garcia Garibay from UCLA. Great talk, Aurora. Thank you so much. The question that I'd like to ask you is connects with the previous talk. So, you know, Kitay-Gorodidsky, one of the things he worked on significantly is mixed crystals. And one of the things came up with is that when you have two molecules with a coefficient of structural similarity greater than 85%, they form crystals. Right? So can one use a similar metric in terms of polymorphism? That, you know, there is a metric which you cannot go into the different crystal energy minimum? I don't know how to formulate it exactly, but it's just so simple.
Here, 1, 2, 3, it's working. You speak like this, okay? Thank you. For all another. Be closer here, not this one. Thank you.
Okay, I know Panche chose me because I'm one of the young participants to speak, but I've been in the field for nearly 20 years. and I just don't know how to predict which compounds will be polymorphic and which compounds won't be polymorphic. It's just one of the hardest questions you can have just based on molecular structure, if that's what you're trying to say. There are lots of work done in my group, Ryan's group, in Sally Price's group, looking at molecules that are very similar. So they're analogs. Okay.
So if two compounds have a coefficient of structural similarity much greater than 85%, they can make the same crystal, they can co-crystallize. Will two molecules that have a similarly high coefficient of structural similarity will have similar polymorphic tendencies? In other words, if I take Roy, less than 85% of the structure in some trivial way, will I see many polymers?
I don't think so. It's so difficult. So what you can, if you do crystal structure prediction, that might give you the landscape. And the landscape might show you which forms are energetically competitive. And in Roy's landscape, all of the forms that were energetically competitive, you could produce. But there are other landscapes that look the same, and there will only be one crystal structure that you can produce. And a lot of it comes back, I think, to nucleation. Nucleation and how, even if whether some of the structures can interconvert easily, so they end up going to the minimum, whereas the others can't. But it's a very difficult question. What I can say is that we can use the structural similarity to make new polymers sometimes. And there is some work done by Sally Price and collaborators where you use this compound that is similar but has a slightly different crystal structure, and you can template your compound on those. And that sometimes, but it's not easily predictable either, gives you new polymorphic forms. And it's all about how you nucleate those and why there are compounds that you can nucleate lots of them, and in other cases there aren't. Because our experiences is that it's the norm that you have lots of different crystal packings that have similar energies. But some systems you can nucleate lots, and some systems you can't. And even if they're similar and they're analogs, the polymorphism behavior may be completely different.
Okay.
I didn't mean that being in the field for 20 years, really didn't mean it.
Thank you, Aurora. So we have 3 people who have caught my eye, so I think the mic is now over there, but I will come back to you. So go ahead.
Okay. Thank you for your presentation. So I'm Gabin Babode from Rouen University, and my question was related to the part which was linking hydration and conformational polymorphism. Okay, I don't remember if you come from the hydrated form, and if you heat up, did you come back to the 2 forms, or from A and C?
Just the form that has the greatest similarity. Yes, I don't think I said that, but yes, you're right to ask. So, It's the same behavior. So the form that will hydrate faster to the hydrate is the form that you get when you dehydrate the hydrate.
Okay.
So that's right. And there is a very strong link in conformation. It is not just conformation. Conformation is just one part of the story.
Yeah.
It's also thermodynamics, so there's a lot to it. And in the paper, we go through all of the facts related to these conversions. So it's not just conformation. Conformation in this case is just one more aspect, but it's not just conformation.
Thank you.
Okay, so one question there, and then Craig, I think, had a question, so we'll come back to you. Go ahead.
Good evening, everybody. Thank you, Aurora, for your in-depth review. I'm eager to justify for myself the concept that we come across the introductory part, that conformational polymorphs much probably exert co-crystals. If I'm eager to hear from you, have you already tested this your concept of multi-component systems when conformational polymorphs co-crystallize with co-formers? Doesn't matter, it's going to be molecular crystals, salts, or co-crystals. Because so far, in the introductory part of the articles, we come across mostly of trial and error attempts for getting even elusive polymorphs toward the co-crystallization. I think this is emerging issue for being tested.
So let me rephrase your question, because I'm not sure I understand. You talking about impact of flexibility on co-crystals?
Yeah. Toward the co-crystallization, because it's two concomitant effects of crystal packing with one kinetics and also solvatation or...
Yeah, so there are obviously lots of applications of molecular flexibility in the solid state that I haven't touched upon. One is exactly the impact of flexibility on making co-crystals. Again, lots of the papers that we see on co-crystals tend to be rigid compounds because they're academic papers. So it would be so interesting to see more flexible compounds that are able to make co-crystals, and what can we learn from those? But I haven't looked at this data, so I wouldn't be able to comment. But I could imagine how flexibility might be a problem in the formation of co-crystals, but I don't know. I don't have the answer to this question. But we see that flexible compounds can make hydrates and solvates quite easily and can change conformation. So it wouldn't surprise me if in making co-crystals, you may also find lots of conformational co-crystals of these systems. So that wouldn't surprise me. There's another thing I haven't talked about, is the impact. I've seen Simon today, and I thought like, oh, I should have thought about this before. But pressure will also impact conformation. I think there's some work on piracetam where the conformation switches, and you can only get that by pressure. So there are so many other fields where this topic keeps coming up. And that's another one. Also chemical reactions that we heard about, how the conformation will impact the chemical reaction, or with the chemical reaction or the phase transition is occurring, what is the conformational changes that we see? So it's everywhere. So the more complex our compounds are going to be, and we're going to work with, and the future of the solid state is some flexible compounds, I'm sure of this, then the more we need to consider these things. I hope I've vaguely answered the question.
Thank you.
I would just like to give Craig a chance to ask his question, and then I think there's a question at the back there.
I'm not sure I have a question or a comment. Well, the question is, the temperature seems to be missing in all of this. What is the thermal distribution of conformers in the gas phase and in solution? Is one question that comes to mind. Another one is, what do the thermal ellipsoids look like in the different conformers? And that, of course, relates to the vibrations. And there, it seems to me, if you really want to study the potential energy surface of the crystal, what you need to do is look at the low frequency vibrational spectra.
So You're absolutely right. We just look at 0 Kelvin, but sometimes the energy barriers that we see at 0 Kelvin might not exist at room temperature. And this is so. And actually, the biphenyl, you still see the barrier, but we do tend to do so. When we looked at the crystals in action part of the problem, if you cool down to really low temperatures, then these conversions between conformations completely freeze. And as you heat up, then you start to see this becoming a dynamic effect. And these are obviously conformers that have a very low energy barrier that virtually disappears once you heat enough, and the crystal expands slightly.
But also, it seems to me that there should be more DSC done.
Okay. Yeah, so coming back to your talk, I'm pretty sure there will be transitions in forms that will be driven also by intramolecular pushes and pulls. But yeah, that's another area we should be looking into.
So this is turning into a Faraday discussion now. So I think it reflects the level of interest in this topic. There's a question right at the back, and then I think I caught somebody else's.
No one's hungry?
Go ahead.
I'm Maggie Lingenfelder from EPFL. Thank you, Aurora. Yes, I'm hungry. I think everybody is, but your talk was really wonderful, so thank you so much. You show us the challenges of using DFT to tackle this problem. Of course, it's an ab initio method. I wanted to ask you if you could share your thoughts on using machine learning in this problem.
Well, your machine learning is going to be as good as your data to train your machine learning is. So I think that's the answer. If you train your data on DFT only, you won't be able to predict conformation of polymorphs. But so you're going to have to use the MP2 methods. You're going to have to use. So get the best modeling you can, and then fit your machine learning models.
Okay, so
thank you.
Question, yeah. So you've got the mic, and then
yeah. Thank you for the beautiful talk. I'm Luca Grisanti from Ruđer Bošković, Zagreb. I just wanted to ask one thing about modeling, because as you mentioned that the work has been, the efforts has been toward improving, like from DFT to dispersion corrected, and then delocalization. But right, how about going from potential to free energy? So considering all the effects of the other motions and the other were mentioning here. So in practice, wouldn't it be better to look more at the other effects other than improving the accuracy of the single 0 Kelvin calculation when one does crystal structure prediction?
If you don't get the 0 Kelvin right, you're not going to get the temperature right either. So I think the issue with the issue of trying, so again we go back to the issue of temperature. So even the free energy calculations that some modelers are doing right now are based on the harmonic approximation, which is also a big approximation. So I think one needs to understand the limitations, and it's just easier not to talk about temperature. I know you want to, but it makes things slightly easier. But modeling free energy phonons in crystals is extremely complicated, and if you don't get the conformational energies can be off by 4 or 5 kilojoules per mole. That's massive. So even if you adjust your free energy by 2 kilojoules per mole, your conformational energy error is going to be so large. So I do personally think we need to get the conformational energies right. And once we get that right and the models right, then the phonons, but the phonons make a big difference too, with temperature, obviously. But again, this is a big challenge. But I think you should talk to Graham Day, because he's the expert in the room on that.
Okay, so go ahead.
Thanks, Aurora. Simon Parsons, University of Edinburgh. You'll remember last year, about this time, the news was full of the advances that have been made on protein folding, another very conformationally flexible problem. And the question before the last one sort of made me think of that. And I wonder whether you think the approach that was adopted there, which was, I think, machine learning and artificial intelligence, though I think I've just told you everything I know, do you think that is
applicable to the kind of conformational problems that you're talking about here?
Well, it's an excellent question. We saw how with biphenyl, you had a minimum driven by intramolecular energy and a minimum driven by intermolecular energy. So the best thing is to have good experimental data. That is definitely the best thing. So in protein folding, they fit the machine learning to the experimental data, of course. And probably that has been why it's been successful. But what you see experimentally might not be the lowest energy minimum. In fact, Grimes' paper shows that. So, but do we have enough data? That's the problem. Because to fit a good machine learning model, you really need a lot of data. And if you don't have a lot of data, and if you don't have good data, it doesn't matter, this machine learning is going to be not good.
So just following up on that, and do you think the success of the protein folding exercise last summer, all that research, is really dependent on the chemical similarity of proteins? I mean, really, you've got 20 amino acids, and the bonding and the chemistry, I suppose you could argue, is limited.
So is this the deep learning? Is this the DeepMind paper?
Yeah,
Are you talking about?
Yeah. And, whereas for a general chemical system, it's much more diverse. So
Yeah.
Do you think that's?
I totally agree with you. I don't think we have enough data, even in the CSD with over 1 million crystal structures now. I don't think we have enough data, especially if you need to be digging down into specific chemistry. Yeah, I completely agree, Simon. It's a great comment.
Okay, so I think the food is getting cold. Everybody ready to go? We're good? All right, so let's stop here. Thanks, Aurora.